I must admit a little bit that to tell you what I do in 20 minutes is a very difficult exercise. I am teaching a graduate course at the moment. Well, it's just finished, but it meets for 4 hours. So I'm much more comfortable talking for 4 hours on a Thursday than I am talking to you for 20 minutes. So excuse me if I refer to my notes from time to time, because I want to stay according to the essence of the complementary nature, which is tick and tock, the clock. This sculpture that you see is called Hands Across the Divide. It stands at the end of the Craigavon Bridge in Derry, in the north of Ireland, the place where I'm from. And it symbolizes, of course, hope. Hope for the end of division and fragmentation. Hope for the end of conflict. And this, the sculpture resonates, I believe, with the Noor Foundation, which Richard described earlier, which aims to cultivate greater understanding, tolerance, and unity among the people of the world. And I'm very grateful to Jim Giordano and Richard Rass for the invitation to come and speak. So what can science, and in particular brain and behavioral research, do to end conflict and promote global harmony? The answer, to be quite honest, is not much so far. Despite all the successes of contemporary neuroscience, despite the fantastic developments in neuropsychiatry and neurology in terms of treating neurological diseases and so on, even removing the very stigma of mental illness and epilepsy, not much has changed. If you look around the world, you'll agree that us human beings have not changed in any fundamental sense. If you look at wars, look at it, wars, poverty, violence, rape, greed, permeate modern life just as they have for centuries. And all the knowledge about brain research and all our education doesn't seem, in a fundamental way, it's done many wonderful things, but doesn't seem to have changed us very much. All our knowledge of the brain has not led to much wisdom or deeper understanding of ourselves. To turn knowledge into wisdom is a kind of alchemy that has escaped us. What can we do to change that? To change ourselves? To say that we need a new perspective or a new awareness, to become aware and so on, is hardly a novel idea. There have been plenty of therapies and recipes over the years for human change, but they haven't got us very far. Perhaps the reason is, actually, even though we use the words a lot, they weren't actually grounded in science or in scientific principles. So here's the big problem. Arguably the hottest and most important problem in science: how does the brain work? And what is its relation to mind and behavior? Specifically, how are the parts of a complex system, like the brain, coordinated, hence the word coordination, both in space and time, so as to produce the intricate functions of action, cognition, emotion? We hear a lot these days about genes and molecules, but how does one human brain or human being coordinate or entrain, as Professor Donald nicely put it, or resonate with another? We may not realize it, but we live, I hope, come back, oh dear. We live in a world of coordination. At every level, at every scale of endeavor. I'm just going to, oh dear. Well, these are many different levels: humans, neurotransmitters, ion channels, dendrites, neurons, brain areas, brains, organisms. And the problem of coordination I like a lot, because it's sort of like gravity. It's so familiar that we take it for granted. And the problem of coordination ignores the boundaries between disciplines and scales that we seem to have set up. Nothing is more important than coordination. Patti's remarks here are very pertinent, and one could add that for understanding our brains, our minds, our behavior, our societies, our cultures, ourselves, the problem of coordination is crucial. In this talk, and I have to move quickly now, I want to tell you about a beautiful equation. I want to do something that is really very strange, that describes basic patterns of coordination between the parts of the body, between stimuli and responses, even between people and brains, as if people are interacting with each other in a dance. As I said, we may not realize it, but we live in a world of coordination, and this is the problem. So I am interested in grounding the problem of coordination in mathematical understanding. The equation that we will examine together describes the coordination between different kinds of things. You can replace the components or substitute one thing for another. In this sense, the equation describes the coordination behavior itself. So stay with me on this and how that coordination arises. The physical nature of the components really only determine, as it were, the space of existence. They don't really come into this. This equation that I'm going to show you, it's only one equation, so don't get scared about the mathematics, has been tested over a period of 25 years. And although it's been extended and elaborated for other kinds of things, here I'm going to just discuss with you, share with you, its basic elementary form. I won't be presenting complicated mathematical formula or anything like that. I'll show you what it looks like, and it's not any more complicated than F equals ma and so on. The point is that when you look into this equation, which describes coordination in living things, what it is telling us, I hope, will allow you to see that there are some new possibilities, a different picture of reality, one in which the friction of opposites, the ubiquity of contrarieties, the taking of sides, which seems so rooted in our blood, is put in a different perspective. The equation, which I say is based on strong experimental evidence, shows us how the dominating either-or, you saw in the last slide, mode of description, can shift and transition to a different pattern, a different mindset, a shifting reality, one that allows you to see the nature of things has more to do with both and neither nor. I call this shifting reality the complementary nature. To cut to the chase, the bottom line is that a deep principle of complementarity, I think, underlies life, brain, mind, and society. Thinking in terms of contraries is very easy. The either-or is terribly easy to us when life is simple or we think it's simple. But the claim on the floor, the claim that I'll make to you, is that in complex coordinated systems, sharp dichotomies and contrarieties will have to be replaced by far more subtle and sophisticated complementarities. In the science of coordination that I'll discuss, we have a science that gives us useful, accessible information, entry into the wisdom of the ages. If only we can get out of the narrow and rigid worldview that rests on fixed points and the contrariety of the either-or. So let me begin with a story. And it's a well-known anecdote about the very famous physicist Richard Feynman. And don't worry about the slide, it's only a dummy slide, so just pay attention to the story, the narrative. Actually, I think this appeared in the New York Times recently or something. Anyway, it doesn't matter. So Feynman was trying to avoid the draft, and a medical examiner came to him and said, Mr. Feynman, show me your hands. And the medical examiner was looking to see if Feynman would, be an open person, show his hands up, or a closed person with his hands down. Well, Feynman did this. And then the examiner said, well, turn your hands over. No, the other way. And Feynman did that. But let me, with this little example, do a little experiment with you all. So what I'd like you to do is actually just start in the Feynman posture, right? But now we'll do this rhythmically. This is a little act of coordination. And you can all do that, Okay, stop. You can also do the pattern that the psychiatrist wanted, open, close, like that. You could do both of those things. Very clever. Huge brains can do that. But now, go back to the Feynman posture and start with one palm up, one palm down, and just speed up a little bit. Speed up a little bit. Speed up a little bit. Ah. What happens, you see, is that there's a transition happens. And this is all very interesting, because it shows you in the first instance that you can do both in phase or antiphase, either one or the other, depending on what I tell you, and that you can certainly do the in phase one over a whole range of rates or parameter values, as we might say. But the interesting thing is that when you start in this antiphase pattern and just speed up, even Richard Feynman would have switched to what the psychiatrist wanted. Yeah? Is this kind of coordination restricted to dumb hand movements? Not really. You see the same when you look at the coordination of the brain. And in fact, in this moving quickly, here is an example actually from Science magazine not very long ago, where you see that the parts of the brain, and this is a cat, looking at the same object, actually parts of the brain move in phase with each other. Synchronous impulses. And if you look at this, there are about 8 ups and downs every 200 milliseconds, and that's 40 times a second. So there's something perhaps important in that. But this whole idea here, you see, is that the neuroscientists, you can see the title. So this is just in-phase coordination, yes? The title is already the mind revealed, and neuroscientists refer to this as binding. Notice this binding was so excited that the editors of Science called it the mind revealed. Now, coordination is a little bit more complicated than that. So here's another example from the late Francisca Varela, who's also interested in these matters that James has discussed with us. The data in this case, and I won't take you through all this, it shows raw data that's appropriately processed, and then you can see these are parts of the brain, and what you see is that they are not coordinated, and then they just lock in temporarily. Thank you very much. You go. They lock in temporarily, and but the key point that you can see here is that this isn't sort of like a regiment marching. Actually, the parts of the brain are sort of random and independent, and then they just come together. Then they break apart, they just come together, then break apart. So this is a very beautiful kind of dynamic where neural groups come together, leave, depart, return again, and so on. Now, actually, the very same phenomena can be seen when you take 2 brains and 2 people. And this is a very simple experiment. It was published in the Proceedings of the National Academy of Science. Again, I won't go into all the details, but think of the technical achievement here of recording simultaneously from 2 brains as they are interacting with each other. Now, the key part of the experiment is initially they are told, just move, each one is told, just move your finger up and down as if you're going to do it all day. And then a liquid crystal display becomes transparent and they see each other's hands. And what happens when that happens is that, as Professor Donald mentioned, they entrain to each other spontaneously. So these are some of the patterns that you see. Again, I can't go into all the details, but if you look on the left part of the picture, you'll see that some people, we call it social neglect, even though they see each other, they keep doing their own rhythm. They do their own thing. Whereas others, you can see initially on the left side, this side here, they're not coupled at all, but then they couple in phase with each other, just like the hands. Am I bothering you? Or they coordinate anti-phase. So you see, actually, exactly the same set of patterns. Now, this is poetry in motion. Coordination in the brain is like a Balanchine ballet. Neural groups briefly couple. Some join as others leave. New groups form and dissolve, creating fleeting coordinated patterns of mind that are always meaningful but don't stick around very long. But in reality, what have we got here? We've got this in hands, neurons, brains interacting with each other. What have we got here? What has nature given us? Well, these are the phenomena. You see coordinated phase and frequency locked states. Neuroscientists refer to these as functional integration. Neuroscientists, everybody loves to create their own language. Binding, dynamic linking. You see no coordination, which is segregation, independence of neural populations. You see transitions of the kind that you experienced, a kind of dynamic decision-making. Who was deciding there for the switch? Yeah? You see this partial coordination of transient tendencies to couple, coexist with tendencies of components to remain independent. And people talk about that as highly neurally complex. Science seeks to come up with theoretical models that will try to explain as broad a range of phenomena as possible in order to understand things. And this is what we're going to do. Now, what concept will we need to use here? We'll need to introduce a concept. A concept from complex systems is called the order parameter. I could give you a long lecture on this notion. It also has other names, a collective or coordination variable. So think of the physical example that you all experienced. What would be the coordination variable there? A key aspect is that it's meaningful and relational. It spans or unfolds different domains and so on. It does, as it were, does something very special. It eliminates sort of the Cartesian cut. It eliminates the arbitrary division between things, and it's contextually dependent and so on. You know, this little box on the right, you see that somehow this order parameter is created from the interaction of the components, but it in turn modulates those components. That's the key idea of reciprocal or circular causality. Yeah? So ask yourselves, what would be the order parameter in all these different cases? Here's the basic equation. Okay? The basic equation is written in terms of phi. Phi is just the phase relation. Remember, in phase, antiphase. Phi. Okay? This delta omega actually has to do with differences between the component parts. Whether those parts be people, parts of their brains, parts of individual brains, and so on. And it has a stochastic term, what we call a noise term. So for the experts, this is a nonlinear differential equation with stochastic noise. So that's really nice, yeah? That's what you came to hear about at the top of the, where the United Nations, or where are we? No. So this basic equation, like other equations in science, is a beautiful equation. It defines how the coordination state of a system, as observed through a relevant collective variable, evolves over time. Let me visualize it with you. Let's look at this. Forget the mathematical nomenclature, but get the intuition. Mathematics is not just about notation. It's about intuition. And here what we're trying to do is actually map all the phenomena that we described onto a theoretical model. And the way we do that is we take this order parameter and we look at how it changes over time and we plot it against itself. That's all this is. It's a function. And where this function crosses the line, that tells us where the fixed points are. So this tells us, yes, there's a coordination state at in phase and there's a coordination state at antiphase, and those are stable. And surrounding those stable points where the slope is negative, you have a positive slope where these are unstable. So this is basically a partnership between the stable and the unstable. So you already see on the left-hand side here that this would account for the fact that neural groups or hands or people could coordinate in phase or they could coordinate antiphase. Both are equally stable. That's all it means. And this is referred to as bistability, or in general, multistability. And I'll argue, you see, the bistability, it's an essential nonlinear feature, is kind of the basis of polarity. of polarization. This is the either-or, either in phase or antiphase. Yeah? So now you change the coupling between the components, and what happens here is that the state at antiphase disappears. That's the disappearance when you were speeding up. You switched from antiphase to in phase, and that's what this one is. This one is gone. There's no longer any state at all, coordination state, only one near in phase. So this gives us transitions. It gives us decision making. We had two possibilities, and we switched to one. And then there is this sort of beautiful place on the right-hand side where there are no longer any coordination states at all. There's no longer any stability. But the beautiful thing is that there is still attraction to where these fixed points used to be. The whole function is lifted off the line, and now you just have attraction to where they were. The ghosts of the fixed points are what governs this tendency for the system to come together, like a marriage, the tendency for the parts to do their own thing. Get it? Tendency for the components to come together, and a tendency for the parts to do their own thing. And that happens at the same time. So whereas we could call this, as a neuroscientist, these are integrated coordinated states, functionally linked and so on, we could talk about switching, and neuroscientists would say, where's the switches? This is a dynamic phenomenon. Here you see a tendency for the parts to integrate, to come together, coexists with the tendency for the parts to behave autonomously. Tendency for the parts to do their own thing. Quite astonishing. And that equation covers all the phenomena that I showed you and many more. Okay? So I could show you this in time, and I think in the interests of time, I will not. But I could show you how these polarized states are created and how they disappear. And I'd be happy to do that after the talk later on. I won't show you these lovely simulations, but I want to convey the message. That is, coordination, segregation. One theory of the brain is that it's highly modular. All neural groups function independently. They do their own thing. That's like the parts not being coordinated at all. On the other hand, you might think, well, if all the neural groups are coordinated together, it's almost like epilepsy, highly integrated. These are the two polarities here with respect to brain theories. These are the two different views of brain function that dominate our understanding of ourselves, our own brains. And then you see, well, some could come together, some independently. And then what this little mathematical equation shows you, that some come together at the same time as some go apart simultaneously. Yeah? Beautiful little equation. Yeah? So, in the literature, this metastability, meta meaning beyond, is an entirely new conception of brain functioning. You won't read about it in the New York Times, I don't think, for quite a while. But it's a conception where the individual parts of the brain, you can read this for yourselves, exhibit tendencies, not states, tendencies to come together autonomously at the same time as they exhibit tendencies to function as a coordinated unit. And of course, since we here are interested in the relationship between the arts and the sciences, my friend from Derry, where I'm from, Seamus Heaney, already got it. He already grokked it. He grasped the concept. Of course, the difference here is that we've put this concept on a very firm, empirical, and mathematical basis. So when we're talking here about complementarity, it is not just a word. But poetry is more a threshold than a path. One constantly approached the coming together and constantly departed from, at which reader and writer undergo in their different ways the experience of being at the same time summoned here and released. Yeah? Beautiful. So, here's our little equation, and it gives rise to these complementary pairs. I've discussed this integration segregation tendency, but the very beautiful aspect of this is that this equation already has individual and collective as part of it. The parts and the coordination go together. It has choice, because this coupling aspect gives you determinism, it gives you choice, and it also gives you chance. It gives you cooperation, and it also gives you competition, because the parts are, as it were, quarreling with each other at the same time as there's a tendency for them to